Welcome back to Notes of Curiosity, exploring ideas that matter. All right, let's unpack this. Today we're diving into symmetry and asymmetry.
And we've got a great guide, Nobel Prize-winning physicist Tsung-Dao Lee.
Yeah, his work is really fascinating. We tend to connect beauty with symmetry, but Lee's work suggests asymmetry can be even more profound, and we've got some awesome material to dig into.
Yeah, you've provided excerpts from Lee's biography on nobelprize.org, his Nobel banquet speech, even an interview.
Right. And of course, we can't forget his book, Symmetry and Asymmetry. So before we get into all that, who was this guy? Tsung-Dao Lee. It's not exactly a household name.
Well, his story's fascinating. Born in Shanghai back in 1926, had his education disrupted by World War II.
Oh, wow.
Imagine having to teach yourself physics before even going to college.
Talk about a self-starter. But he obviously did all right for himself. And ending up at the University of Chicago,
Oh, yeah?
mentored by another physics giant, Enrico Fermi.
Yeah, and Fermi had this really unique teaching style, almost encouraged students to teach him. He'd say things like, Lee, why don't you look this up and give me a lecture next week?
Wow, I love that. Really builds confidence, encourages deep thinking.
Exactly. And you can see how that influenced Lee. But what really put him on the map in the physics world was his work on parity violation.
Okay, gotta admit, I'm a little fuzzy on what that actually means.
It boils down to this. For a long time, physicists assumed that the laws of physics would be the same
Okay,
if you flipped everything around in a mirror. This is the concept of parity.
gotcha.
But Lee, along with his colleague Chen-Ning Yang, they realized there was any real experimental evidence to support this, especially when it came to weak interactions.
So they basically questioned one of the fundamental assumptions of physics. Pretty gutsy.
It was. And their questioning led to a series of experiments, most famously the Wu experiment, which proved them right.
Wow.
Parity as a universally conserved property was out the window, and at just 30 years old, Lee became one of the youngest Nobel laureates in physics.
It's an incredible story. Okay, but let's get to the heart of symmetry and asymmetry. What's the core idea here?
Lee argues that asymmetry can be just as profound, even more interesting than perfect symmetry. He uses this great example of a little girl trying to read a book that's reflected in a mirror.
I'm intrigued. What happens?
She's completely bewildered. The words are backwards. She can't make sense of them. And that's Lee's point.
Okay.
A perfectly mirrored world, seemingly symmetrical and beautiful, wouldn't actually function the way ours does.
That's a really clever way to illustrate that. And it makes me think of something Lee said. Symmetry, as wide or as narrow as you may define its meaning, is an idea which has captured the imagination of mankind for centuries. But he's trying to broaden our understanding of it, to go beyond just the visual.
Absolutely. He even had a fascinating conversation about this with Chairman Mao Zedong.
Wait, Chairman Mao debating physics best with a Nobel laureate. Okay, that's an image. How'd that go?
Well, Mao wasn't a big fan of symmetry in physics. He preferred a more dynamic view of nature. But Lee brilliantly demonstrated that even dynamic processes have a kind of symmetry. Used a simple example. A pencil rolling on a tilted book.
Okay.
It's constantly moving, but the overall process still exhibits symmetry. It's like Lee was saying, look, even in change, there's an underlying order.
That's really interesting. It's like he's revealing these hidden patterns we might not notice. So how does this asymmetry idea play out in nature and art? I mean, those are pretty different realms.
He gives some captivating examples, contrasts the beauty of an asymmetrical natural landscape with a perfectly symmetrical piece of artwork, argues the natural landscape feels more alive, more engaging, and then he gets into these intricate Chinese window lattices.
Oh, they are beautiful. You're saying there's a deeper meaning to their symmetrical pattern.
Absolutely. He connects them to ancient symbols like the swastika, also known as the gemadion, which appears in tons of cultures. He points out these symbols, while having rotational symmetry, don't have mirror symmetry. It's those subtle nuances that highlight the complexities of symmetry and asymmetry.
So it's not just about if something looks the same flipped, right? There are different types of symmetry at play. I'm starting to see things in a whole new light.
And it gets even more fascinating when Lee brings in something called scaling symmetry.
Scaling symmetry, Aki. You've lost me.
Think of a seashell. That spiral shape follows a mathematical pattern where the size changes,
Okay.
but the basic shape stays the same. That's scaling symmetry in action.
Ah, so like zooming in or out on a fractal.
Exactly. And Lee points out that turbulent flow, like in Hokusai's The Great Wave off Kanagawa,
Right.
also exhibits scaling symmetry. It's like nature has this code for creating complex structures from simple rules.
Okay, my mind is doing backflips. So we've got asymmetry being more interesting than perfect symmetry. And even dynamic processes can have symmetry. Where does Lee take us from here?
He tackles another fundamental concept, mirror symmetry, or what physicists call parity. And he uses a simple but profound example that of a girl trying to read a book reflected in a mirror.
Oh, right. The letters are all backwards. I remember that one.
Yeah.
So what's Lee getting at?
He's highlighting the difference between our perception of left and right and the actual laws of physics.
Okay.
For a long time, physicists assumed those laws would be the same in a mirrored world. But Lee's work on parity violation shattered that assumption.
It's like he's saying our everyday experience of left and right might be completely different from how the universe actually works.
Exactly. And that's where things get really mind-bending. Lee dives into this subtle but crucial distinction between symmetry in the laws of physics and symmetry in the actual state of the world.
Okay, now you have to unpack that for me. What's the difference?
Think of it like this. The laws of physics themselves might be perfectly symmetrical, meaning they don't favor left over right.
Okay.
But the actual arrangement of matter in the universe might be asymmetrical.
So it's like having a perfectly balanced scale, but then putting more weight on one side.
Perfect analogy. Lee argues this might be the case with our universe. The laws of physics might not inherently favor matter over antimatter, but for some reason our universe ended up with more matter, and that's a huge she question.
Wow, this is making my head spin. So we've got symmetry in the laws of physics versus symmetry in the actual universe. How does Lee connect that to parity violation?
He argues that the discovery of parity violation in weak interactions might be a clue that the laws of physics themselves are not perfectly symmetrical.
Oh, wow.
It's like a crack in the mirror, revealing a deeper asymmetry at the fundamental level.
Whoa. Are you saying the universe might have a fundamental handedness, a preference for left over right?
That's one of the profound implications of Lee's work. It challenges our assumptions about reality, raises fascinating questions about the nature of time, even the possibility of time travel.
Time travel. Now you're speaking my language. What does Lee have to say about that?
He uses a poem to illustrate the puzzle of time reversal.
Okay.
Someone could know. But since T does not hold, I may never be told.
All right, that's a little cryptic. What's he mean by T does not hold?
T refers to time reversal symmetry, the idea that the laws of physics should be the same if time ran backwards.
Got it.
The discovery of certain processes that violate this symmetry raises huge questions about time itself.
Wait, you're saying time might not be as straightforward as we think?
Lee's work suggests that time might not be a simple arrow pointing from past to future. It might be more complex, with subtle asymmetries that have profound implications for how we understand the universe. It's almost like time itself has a kind of shape, and that shape isn't perfectly symmetrical.
Okay, my brain is officially bending. Tell me more about this shape of time. What does that even mean?
Well, it's complex. But Lee uses this analogy of a movie. Imagine watching a film forwards and then backwards.
Right.
In most movies, you'd immediately know which direction was the right one.
Right.
Certain events, like a glass shattering, just wouldn't make sense in reverse.
So you're saying the universe, like a movie, might have a direction, a flow of time that isn't perfectly reversible.
Exactly. And the fact that certain processes in physics violate time reversal symmetry supports this.
This is getting seriously deep. I'm starting to see how Lee connects these abstract ideas about symmetry to some of the most fundamental questions about reality. But where do we go from here?
Well, Lee takes us even further down the rabbit hole, exploring the connection between symmetry and what physicists call unobservables.
Unobservables, is that like invisible stuff?
Not quite invisible, more like quantities that can't be directly measured. Lee uses the example of absolute position and absolute velocity.
Okay, I'm following.
According to the laws of physics, only relative position and relative velocity matter. You can't measure the absolute position or velocity of something in the universe, only its position and velocity relative to other objects.
So saying, I'm standing 10 feet away from you is meaningful, but saying, I'm standing at the absolute center of the universe isn't.
Precisely. And Lee connects this to symmetry. Argues that these unobservable quantities are related to certain symmetries in the laws of physics.
Wait, so you're saying that symmetry is connected to things we can't even measure?
That's what he's suggesting. He's pointing to a deep connection between the abstract math concept of symmetry and the very fabric of physical reality.
This is blowing my mind. So if symmetry is connected to unobservables, what about asymmetry? Is that connected to things we can measure?
That's a great question, and Lee tackles it head on, exploring the relationship between asymmetry and observables. He puts it really well. Asymmetry, on the other hand, implies observability.
Okay, I'm really interested to hear how he connects those two.
Lee uses the example of broken symmetry to illustrate this point. Imagine a perfectly symmetrical object, like a sphere. If you apply a force to it, you can break its symmetry,
Okay.
cause it to deform into a new asymmetrical shape.
So like dropping a perfectly round ball of clay, it hits the ground and splatters into this irregular blob.
Exactly. And that irregular blob, with all its asymmetries, tells us something about the forces that acted upon it. The same principle applies to the universe. The asymmetries we observe, the distribution of galaxies, the prevalence of matter over antimatter, might be clues to the fundamental forces and processes that shaped the cosmos.
So it's like cosmic detective work. We're looking for clues in the asymmetries of the universe to understand its history and evolution.
Precisely. And that's where Lee's work on CP violation comes in.
CP violation. I need a little refresher. Was that again?
CP stands for charge conjugation and parity. It's a combination of two fundamental symmetries: charge symmetry, C, which deals with the interchangeability of matter and antimatter,
Okay.
and parity, P, which, as we talked about earlier, is related to mirror symmetry.
Right, so CP symmetry would mean the laws of physics are the same if you swap particles for their antiparticles and you flip everything in a mirror.
Exactly. For a long time, physicists thought CP symmetry was absolute. But Lee's work, along with experiments that showed certain particles decay in ways that violate CP symmetry, challenged that.
So CP violation means there's a fundamental difference between matter and antimatter, even beyond just their opposite charges. I'm starting to see why this is a big deal.
It is a big deal. And Lee argues the CP violation might be one of the key reasons why our universe ended up with more matter than antimatter.
Hold on. You're saying this tiny asymmetry in the decay of some particles might explain the existence of, well, everything.
It's one of the leading theories, and it's a testament to the power of asymmetry. Even a slight imbalance can have huge consequences on a cosmic scale.
This is mind-blowing. So we've got asymmetry linked to observables, CP violation as a potential explanation for the matter-antimatter imbalance, and even hints about the evolution of the universe. Where does Lee take us next, T?
Next, he dives into an even more mind-boggling concept: the vacuum.
The vacuum, you mean like empty space? What's so special about that?
Lee challenges the traditional view of the vacuum as simply nothingness. He argues the vacuum is actually a dynamic entity, a physical medium with its own properties, and even energy. He says the vacuum, however, is far from being empty.
Wait, are you saying that empty space isn't actually empty?
That's exactly what Lee is suggesting. He draws on concepts from quantum field theory, where even without particles, there are fluctuating fields that can create virtual particles and antiparticles.
Okay, this is getting seriously weird. Virtual particles. Fluctuating fields. Those sound like something out of science fiction.
It's definitely deep stuff, but Lee explains it in a way that's surprisingly accessible. He uses the analogy of a boiling pot of water.
A boiling pot of water. How does that relate to the vacuum?
Think of the bubbles that form in boiling water. Those bubbles represent virtual particles popping in and out of existence.
Okay.
They're not real particles in the sense that they don't last very long, but they have a real impact on the properties of the water, or in this case, the vacuum.
So empty space is like this constantly bubbling cauldron of virtual particles.
That's a great way to visualize it. And these virtual particles, Lee argues, actually have a measurable impact. They contribute to the energy density of the vacuum, which, as we discussed earlier, might be related to dark energy and the expansion of the universe.
Okay, my head is officially spinning. So we've gone from the asymmetry of landscapes to the weirdness of the vacuum and its connection to dark energy. What's next on this wild ride?
Lee takes us even deeper into the heart of matter, exploring the world of elementary particles.
Ooh, okay.
He discusses the fundamental building blocks of matter quarks and leptons and the forces that govern their interactions.
Ooh, this is getting into particle physics. It's always fascinated me, but it can be a bit intimidating.
I know what you mean. But Lee has this incredible ability to explain complex concepts clearly and in an engaging way. He guides us through the history of particle physics, from the discovery of the electron to the development of the Standard Model, the current reigning theory of particle physics.
Lead the way. I'm ready to delve into the particle zoo.
Then buckle up, because Lee reveals some of the most mind-blowing discoveries of the past century: the existence of antimatter, the strange world of quarks, and the elusive Higgs boson.
Wow.
The particle responsible for giving other particles mass.
This is like a crash course in particle physics.
Yeah.
And you're saying Lee connects all of this back to symmetry and asymmetry.
Absolutely. He highlights the crucial role of symmetry in shaping our understanding of particle physics. The Standard Model, for instance, is based on a set of fundamental symmetries that dictate how particles interact.
So symmetry is like the underlying code that governs the behavior of the tiniest bits of matter.
That's a great way to put it. But as with everything else, there are asymmetries lurking beneath the surface. Lee discusses the violation of CP symmetry in the decay of certain particles, which, as we mentioned earlier, might hold the key to the matter-antimatter imbalance in the universe.
It's amazing to think that these tiny subatomic particles hold clues to the grandest mysteries of the cosmos. I love how Lee keeps bringing us back to that interconnectedness.
It truly is remarkable. From the symmetry of a seashell to the asymmetry of particle decays, there's this profound interconnectedness that Lee so elegantly reveals throughout his book.
I'm starting to see the world in a whole new light. Everything is symmetry and asymmetry, from the tiniest particles to the vast expanse of the universe. It's really quite a journey. But we're not done yet, are we?
Not quite. Lee takes us on one final adventure, exploring the frontiers of physics and pondering the big questions that remain unanswered.
This is getting me really excited. What are some of those mysteries that still puzzle physicists?
Well, Lee discusses the quest for a unified theory of physics, a theory that would explain all the fundamental forces of nature in a single framework. He also delves into the mysteries of dark matter and dark energy, and invisible stuff that makes up most of the universe.
Now, those are some seriously big questions. Does Lee offer any potential answers?
He discusses some of the leading theories, but emphasizes that we're still a long way from a complete understanding. He sees this not as a discouragement, but as an invitation, a call for young scientists to embrace the challenge and explore the unknown.
That's inspiring. It's like he's passing the torch to the next generation of explorers.
Exactly. And he reminds us that the journey of discovery is just as important as the destination, even if we never find all the answers. The process of searching, of questioning, and of exploring is what makes science so exciting.
This has been such an eye-opening conversation. We've gone from the beauty of asymmetrical landscapes to the mind-bending concept of the vacuum and the mysteries of particle physics. But before we wrap things up, I'm curious about Lee himself.
Yeah.
What kind of person was he beyond his scientific achievements?
Lee was not only a brilliant physicist, but also a deep thinker and a dedicated advocate for science education. He believed that science should be accessible to everyone and worked tirelessly to promote scientific exchange and collaboration between the U.S. and China.
That's wonderful. It's always great to hear about scientists who are also passionate about education and global cooperation.
Absolutely. Lee's legacy extends far beyond his specific discoveries. He was a true visionary who inspired generations of scientists and continues to challenge us to look deeper, question our assumptions, and embrace the beauty and complexity of the universe. And for those who might be a little intimidated by the subject matter, don't be. Lee was great at explaining these complex ideas in a way that's insightful and engaging.
Yeah, I've definitely felt that listening to you break it all down. It's amazing how he takes us from a simple seashell to particle physics, all while reflecting on symmetry and asymmetry.
He even connects it to art, history, philosophy, like his discussion of those Chinese window lattices.
Right.
And how they're connected to ancient symbols like the swastika.
Absolutely.
Yeah.
Those connections really bring the book to life.
Yeah.
It's so much more than just a physics text.
Exactly. Shows Lee's wide-ranging intellect, his ability to see how everything's connected. Like he said, nature seems to have a predilection for the right hand. Simple statement, but it opens up a whole universe of questions.
It really does. Makes you wonder about the fundamental nature of the universe, and if there's some deeper meaning behind those asymmetries we see.
That's one of the most valuable things about Lee's book. It encourages us to ask those big questions, to challenge what we think we know, and to just embrace the mystery of it all.
You know, one thing that struck me throughout our deep dive is how Lee's work seems driven by this insatiable curiosity. He's always questioning, exploring, pushing the boundaries of knowledge.
Absolutely. And he really emphasizes that. It's not just about finding the answers. It's about the journey, the thrill of discovery.
I love that perspective. Reminds us that learning isn't just about facts. It's about cultivating wonder, a willingness to embrace what we don't know.
Precisely. As Lee said, to stop questioning is to stop discovering. A powerful message for everyone, no matter what you study or what you're interested in.
Well said. So as we wrap up our deep dive into symmetry and asymmetry, what's one thing you hope our listeners take away?
I hope they'll want to explore these ideas more, to pick up Lee's book, to start their own journeys of discovery, and remember that the universe is full of surprises. and that by embracing asymmetry, by looking beyond what's obvious, we can understand the world around us on a deeper level.
Beautifully put. It's been fantastic delving into these concepts with you. And to our listeners, thank you for joining us on this deep dive into Tsung-Dao Lee and the beauty of asymmetry. Until next time, keep those minds curious and those questions flowing.